Okay, good day. So let's have another example for steel members that are subjected to both bending and axial tension. Okay, so for this example, a W10 by 30 tensile member with no holes consisting of 345 megapascal steel with L sub B, or that is the unbraced length, okay, and unbraced length of 3.6 meters, is subjected to the axial service loads of, okay, so we have a dead load of 133.50 kilonewtons and a live load of 222.40 kilonewtons, and to the service moments of, okay, so MD X, so dead load 27.12 kilonewton meter, and a live load moment that is 54.24 kilonewton meter. If the value of the C sub B is equal to 1.0, so okay, we are required to determine if the member is satisfactory. So to determine if the member is satisfactory, we need to check, okay, our interaction formula. So I list down the properties of the W10 by 30 from our database. Okay, so since we have the unbraced length is given 3.6 meters, we need to determine if the member or the section is under, okay, is it under zone number 1, okay, zone number 2, or okay, zone number 3. So we need to compare, okay, the value of the unbraced length to the value of, okay, first the L sub P. So to compute for the value of L sub P, okay, so this is L sub P is equal to 1.76 of Ry multiplied by the square root of the modulus of elasticity divided by the value of F sub Y. Okay, so let us have the value of Ry for W10 by 30. So radius of gyration with respect to the y-axis is 34.8 millimeters. Okay, so we are now to substitute. Okay, we have the value of L sub P is equal to 1.76 of Ry. This is 34.8 millimeters. Then multiplied by the square root of for steel, again, this is 200,000 megapascals. Then the Fy of the section, that is 345 megapascal steel. So for the value of the L sub P, this is 1.76 multiplied by 34.8, to be multiplied by the square root of 200,000 megapascals divided by 345. So this is equal to 1,474.68. 1,474.68 millimeters. So obviously, this is less than our unbraced length. So again, the unbraced length is 3.6 meters, or this is 3,600 millimeters. Okay, so we need to check if it is under zone 2 or zone number 3. So for us to determine if it is under zone 2 or zone number 3, we need to compute for the value of the L sub R. So for the L sub R, so we'll be needing first the value of the R sub TS. So let us compute for the value of the R sub TS. Okay, so from our reference again, we have the R sub TS is equal to, or this is R sub TS squared, is equal to the square root of the moment of inertia with respect to the y-axis, the warping constant C sub W, then divided by the section modulus with respect to the x-axis. So let us just check these properties of W10 by 30. Okay, so let's have the value of the R sub TS squared is equal to the square root of a moment of inertia with respect to the y-axis is 6.95 times 10 raised to 6. Okay, so this is 6.95 times 10 raised to 6. Then to be multiplied by the C sub W, Okay, the C sub W is 111 times 10 raised to 9. Okay, so this is to be multiplied by 111 times 10 raised to 9. Okay, then to be divided by, the section modulus with respect to the x-axis of W10 by 30 is, we have that as 531 times 10 raised to 3. Okay, so this value to be divided by 531 times 10 raised to 3. So computing for the value of the R sub TS is now equal to, okay, so this is the square root of 6.95 times 10 raised to 6. Okay, to be multiplied by 111 times 10 raised to 9. Okay, then to be divided by 531 times 10 raised to 3. And then we take the square root. Okay, that is 40.67. So this is 40.67 millimeters. So we have now the value of the R sub TS for this equation. So we'll be needing also the value of C. But for I-shaped section, symmetrical I-shaped section, the value of C is simply equal to 1.0. So this C. And then the value of our H sub O, H sub O is basically equal to the total depth of the section minus the thickness of the flange. So the total depth of the section is 267 millimeters, and the thickness of the flange of W10 by 30 is 13 millimeters. So this is equal to, we have that as 267 millimeters or less 13. So this is equal to 254 mm. Okay, so I think the elements of this formula are complete. So we can now substitute. This is L sub R is equal to 1.95. Then the value of the R sub TS a while ago, so that value is equal to 40.67. This is 40.67. Okay, then multiplied by the modulus of elasticity, this is 200,000 megapascals, divided by 0.7 of Fy, 345 megapascals. And then to be multiplied by the square root of, so let's have the square root of the value of J. The value of J is 259 times 10 raised to 3 millimeters raised to 4. So that is, so 259 times 10 raised to 3. And then again, so the value of C is simply 1.0 for symmetrical I-shaped section. Then divided by the section modulus with respect to the x-axis is 531 times 10 raised to 3. Okay, so this is multiplied by 531 times 10 raised to, this is times 10 raised to 3. Then the value of the H sub O is equal to 254 millimeters. Then to be multiplied by the square root, the square root of 1 plus, so the square root of 1 plus, we have 6.76, then multiplied by the quantity. This is 0.7 of Fy, 345 megapascals. S sub x is 500. 531 times 10 raised to 3. Then, H sub O is 254 millimeters. Then, all over. Right, so the modulus of elasticity, that is 200,000. Then, the value of J is 259. This is times 10 raised to, times 10 raised to 3. Then, again, so the value of C is simply equal to 1.0. So this quantity is squared. Alright, so let us now compute the value of L sub R. Again, I'll be starting with this term. Then if you are to check our previous videos, so we have examples on how to determine if the member is under zone 1, zone 2, or zone 3. So this is just a recall. Okay, so we have that as 0.7 of 345 megapascals. Okay, multiplied by 531 times 10 raised to 3. Okay, multiplied by 254. Then to be divided by 200,000. Okay, then 259 times 10 raised to 3. So this value is squared, to be squared. Then to be multiplied by 6.76. Then plus 1. Then we are to take the square root. Then plus 1 again. Then square root again. Then we are to multiply this one to the square root of 259. This is times 10 raised to 3 times C, that is simply 1. To be divided by 531 times 10 raised to 3. Then the value of the H sub O, 254 mm. Then to be multiplied by 200,000. Okay, divided by 0.7 of 345 megapascals. Then to be multiplied by, this is 40.67 times 1.95. So we'll be having, the value of L sub R is equal to 4,915.15. Okay, so the value of the L sub R is equal to 4,915.15 millimeters. So 4915.15 mm. So we can now conclude which zone. So the value of our L sub P the value of the L sub P is equal to 1,474. 1,474.68 millimeters. This is less than the unbraced length of 3.6 meters or 3,600 millimeters. But also, less than the value of our L sub R, which is equal to 4,915.15 millimeters. So which means the section is under, so the section for this unbraced length, it is under zone number 2. So since it is under zone number 2, so we'll be using this equation to compute for the nominal moment capacity. Okay, so since it is under zone 2, so we need to compute for the nominal moment capacity using this equation. But before that, we need to compute for the plastic moment, that is the m sub p, which is equal to, that is Fy multiplied by the plastic section modulus, that is the Z. Since if we are to go back on our problem, so the given moments are moments with respect to the x-axis. So this plastic moment should be the plastic moment with respect to the x-axis, and we are to use the plastic section modulus with respect to the x-axis. So we have again Fy is 345 megapascals, or the newtons per I square mm. Then for the property of the W10 by 30, the plastic section modulus with respect to the x-axis is 600 times 10 raised to 3. So this is multiplied by 600 times 10 raised to 3 millimeters raised to 3. So if you are to do unit analysis, obviously, so the remaining units will be in Newton mm, since that is a moment. So for the plastic moment, with respect to the x-axis, this is m sub px is equal to, we have 345 multiplied by 600 times 10 raised to 3. So we can have it as 207 times 10 raised to 6 Newton mm. So we are now ready to substitute. So again, so from our problem, the value of C sub B, again for this example, the value of C sub B is simply equal to, it is simply equal to 1.0. So we are now ready to substitute. Okay, so we have the equivalent of the n sub n is equal to C sub B is 1.0, to be multiplied by our nominal moment capacity. This is the plastic moment, 207. This is times 10 raised to 6. Then minus m sub p, this is 207 times 10 raised to 6 minus 0.7 of Fy, that is 345 megapascals. Then the value of our S sub x, again the section modulus with respect to the x-axis, is 531 times 10 raised to 3. Okay, so to be multiplied by 500. Okay, this is 531 times 10 raised to 3. So for the value of the S sub x. Then to be multiplied by the ratio, the ratio of L sub B minus L sub P, all over LR minus L sub P. So we have the unbraced length is equal to 3,600 millimeters, minus the computed L sub P is 1,474.68. Then to be divided by the LR. LR is equal to 4,915.15 minus the value of the L sub P. Sorry, this is 1,474.68. And it should be less than or equal to the value of our m px. So let us compute for the equivalent of the nominal moment m sub n. So this is so let's start with the proportion of the lengths. So this is, we have 3,600 minus 1,474.68 divided by 4,915.15 minus 1,474.68. And then this value to be multiplied by the quantity of 207 times 10 raised to 6 minus the 0.7 of 345 multiplied by 531 times 10 raised to 3. And then this value to be subtracted from 207 times 10 raised to 6. So minus the answer. Then to be divided by, so if we are to do unit analysis, so this value is in terms of the Newton mm. Okay. So this is in terms of the Newton millimeters. So multiplying 1 kilonewton is to 1,000 newtons. Then multiplying 1 meter is to 1,000 millimeters, or basically divided by 1 million. So the computed value to be divided by 1 million will give us the value of n sub n with a unit of kilonewton meter. So this value to be divided by 1000 squared is 158.34. So 158.34 kilonewton meter. So that will be our nominal moment capacity. And it is less than 207 times 10 raised to 6. So this is the same as 207 kilonewton meter. Okay, so it is less than. So we satisfied that condition. So we may now go back to our interaction formula. Okay, so let us compute for the value of PR, PC. Then we need to take the ratio. Okay, so for our PR, the value of PR is the same as, so since we are doing the analysis under the method of LRFD, so PR is the same as PU, which is equal to 1.2 of the dead load, plus the 1.6 of the live load. So we'll be having the value of the P sub R, or the required axial force capacity. That is 1.2. Okay, we have 1.2 of 133.5. Okay, plus the 1.6 of our live load is 222.40 kilonewtons. So for the value of the P sub R is equal to we have the 1.2 of 133.50 plus 1.6 of 222.4. That is equal to 516.04 kilonewtons. So this is 516.04 kilonewtons. Then for the value of our PC, so PC is the same as we have the P of P sub n, or basically equal to, this is P multiplied by Fy, then multiplied by area gross. So we are using again area gross since for this member with no holes. So the value of the area gross for W10 by 30 is 5,700 square millimeters. So for the value of our PC is equal to 0. Reduction factor for LRFD is 0.90. Fy is 345 megapascals. So again, for LRFD, the value of P is 0.90. So 0.90 of 345, then area gross is 5,700 square mm. So if you are to square millimeters, if you are to do unit analysis, again, megapascals times square mm is Newton. So multiplying, we are to multiply 1 kilonewton is to 1,000 newtons. For the value of the PC to be in kilonewtons. So we have this as 0.9 of 345 megapascals multiplied by the area of the section is 5,700. To be divided by 1,000. This is 1,769.85. 1,769.85 kilonewtons. Okay, so we need to compute for the ratio of PR over PC so that we can choose what is the applicable interaction formula. So for the ratio of PR, divided by PC, so our required force of, or this the PU for LRFD, that is 516.04 kilonewtons, divided by the computed PC is 1,769.85. And this is equal to So 516.04 to be divided by that value. So we have that as 0.29. So let's say we have 0.29. So since the value of the PR over PC is 0.29, and obviously this is greater than 0.20. So we'll be using so the first condition, and we'll be using this interaction formula. So for the case that PR over PC is greater than 0.2. So we have now the value of the PR and PC. So let us now compute for the value of MRX and the MCX. Then again, for this example, if we are to go back on our problem, we don't have a moment. So no moment is given with respect to the y-axis. So the moments are given, so for dead load and the live load, so these moments are with respect to the x-axis. So we can assume this term to be 0. Okay, so for the value of the required moment, okay, this is for the m, or the required moment with respect to the x-axis is the same as the m sub u, since we are using LRFD method. Is equal to 1.2 of the moment with respect to the x-axis, plus that is for the dead load, 1.6 of the live load moment with respect to the x-axis. So we have the moment m sub rx is equal to, we have 1.2 of, again, so what is the value of mdx is 27.12. This is 27.12 kilonewton meter plus, we have 1.6 of the moment live load with respect to the x-axis is 54.24. So this is multiplied by 54.24 kilonewton meter. Okay, so for the value of the m sub rx is equal to, this is 1.2 of 27.12, okay, plus the 1.6 of 54.24. That is equal to 119.328 kilonewton meter. Then for the value of our m sub cx, so m sub cx is basically equal to the p multiplied by the value of the m sub n. So reduction factor again for LRFD, that is 0.90. So again, our section is under zone 2, and for zone 2, its nominal moment capacity is 158.34 kilonewton meter. So this is to be multiplied by 158.34 kilonewton meter, and this is now equal to, this is 0.9 of 158.34 kilonewton meter. This is 142.506. So we have, this is 142.506 kilonewton meter. So we are now ready to substitute all these values to our interaction diagram. So again, so since the PR over PC, PR over PC is greater than 0.2, we'll be using the ratio PR over PC, plus, this is 8 over 9 of the quantity, the required moment with respect to the x-axis, divided by the m sub cx, plus, the moment with respect to the y-axis, mry, divided by the moment, this m sub c y, and it should be less than or equal to 1.0. So we'll be using the first interaction formula. So again, for this problem, we don't have moments with respect to the y-axis, so this is I0. So we are now to substitute. Okay, so this is 516.04 kilonewton meter. Okay, to be divided by 1,769.85. Okay, plus we have 8 over 9 of, so since this is 0, MRX is 119.328 divided by our M sub CX. The M sub CX is 142.506. Then plus 0 should be less than or equal to 1.0. So let us check if the member is satisfactory. This is 516.04 to be divided by 1769.85. Okay, then plus we have 119 point 328 to be divided by 142.506. To be multiplied by the ratio of 8 over 9. Okay, so this is let's say 1.036. Okay, we have the value 1.036, and this is obviously greater than 1.0. So therefore, for our conclusion, so since the required is we are to check if the W10 by 30 is, if it is satisfactory, to carry the given combined loadings. So we conclude that W10 by 30 is not satisfactory. So W10 by 30 is not satisfactory to carry the given loads. So for our recommendation, so we recommend that we can maybe we are to try a larger sections. So this will be our answer and a solution for this given example. Since the required is if we are to check if the member is satisfactory, since the value of our interaction formula is 1.036 is greater than 1.0, W10 by 30 is not satisfactory, and we are to recommend to use a larger section. So this will be our solution for this example.